Good morning. My name is Sebastian Berube, and I am the manager for our Service Line Storage Specialist Architects. I'm joined today by Jeremiah Dooley, the senior manager of our developer advocates. And in this session, we will cover accelerating serverless application development in AWS with AWS and file storage. First, let's start by answering the question, why does storage matter in the world of serverless applications? As containers became more and more prevalent in customers' environment, customers felt more comfortable deploying, managing, operating ever more complex and mission-critical containerized workloads. What we've seen over the last few years is a large increase in deployment of data-heavy, persistent containerized applications. Many customers have started deploying workloads such as Elastic MapReduce, Spark, Kafka, Flink, and more recently, we've seen an increase of AI and ML training workloads running in containers. For all these workloads, storage plays a critical role in ensuring high performance, availability, and scalability. As customers scale those types of workloads, storage can also quickly become a significant part of the overall cost of the solution. Additionally, those critical workloads also can become subject to compliance requirements or require predictable data protection, be it backup or cross-region replication. And this is not just AWS customers. The Cloud Native Compute Foundation surveyed customers back in 2020, asking them whether or not they were currently using stateful applications with containers. And 55% of customers answered they already did in production, while 12% said they were evaluating the possibility of doing so, and another 11% were planning to do so in the following 12 months. And that is a total of 78% of customers surveyed that were already running or planning to run stateful workloads in containers. There are three main reasons why modern applications need durable storage. Containers and serverless functions are transient in nature. They're ephemeral. To support high availability and durability requirements for long-running application, we need durable storage to keep the application state. Also, architecting for high availability is easier and often more cost-effective when leveraging storage that offers regional availability. Distributed applications like web serving and ML inference and CI/CD need a shared storage layer to operate. Using shared storage, we can reduce or even eliminate duplicate data that's stored in individual availability zones. Last, data-intensive applications like analytics require fast access to very large amounts of data, which cannot be stored within Lambda function. Modern applications need a scalable storage layer like EFS or S3. Those applications mainly fall in four categories. Developer tools, for example, Jira, Artifactory, or Git, need to share data between instances for high availability, with code and artifacts persisted to multiple AWS availability zones for durability. Content management application like WordPress and Drupal benefit from scaling out to multiple instances for performance and redundancy. They also need to share uploads, plugins, templates across multiple instances. Machine learning frameworks like MXNet and TensorFlow need to have access to data through a file system interface. Having durable shared storage allows several users and jobs to run in parallel on the same dataset, accelerating time to outcome. Shared notebook systems like Jupyter and Jupyter Hub need durable storage for notebooks and user workspaces. Having shared storage allows data scientists to collaborate much more easily. Luckily, here at AWS, we've got a service that's purpose-built to make things easier for our customers. Amazon EFS is designed to be the file storage solution for AWS builders, so they can focus on building. Like S3, it was designed to just work, providing low latency, high throughput, high durability, and high availability. It also implements multiple storage classes and lifecycle policies to enable customers to align cost with workload demands. Many customers use EFS as shared storage for running container clusters, both on self-managed containers running on EC2 or with AWS Managed Container Services. EFS provides shared access to files for all nodes within a container cluster, enabling capabilities such as persistent volumes for stateful container, fast restore for containers in the event of a crash, and fast application scaling to quickly launch new containers as application demand grows, or enable self-service provisioning models. We just recently released the EFS Container Storage Interface, or CSI driver, which is now available as an open source project on GitHub. Also, we have the same CSI driver for Amazon FSx for Lustre. CSI drivers make it easy for developers to use an EFS file system with their Kubernetes service running on either self-managed Kubernetes on EC2 or managed Kubernetes on EKS. Previously, customers wanted to run stateful workload on their Kubernetes clusters with EFS, needed to manually provision the file system, connect them to their Kubernetes pod, maintain the connection as the service scaled and changed. Now, with the EFS CSI driver, it makes it easier, more simple to provision and configure storage for Kubernetes clusters running on AWS. You simply write a Kubernetes storage class and a persistent volume claim to provision. Then reference the persistent volume claim from the pod to use it. It is that simple. If a container is rescheduled on a different node, the CSI driver will make sure that the volume is available and connected when it restarts. So it eliminates the manual provisioning of the file system. This is great news development to make using EFS for container storage even easier.
Yeah, and that using EFS easier is one of the themes that we're going to talk about. So thanks, Sebi. Appreciate you teeing that up so well. Hopefully, after that, we can all see the benefits of the different Amazon storage offerings. But what I want to do now is kind of dig into some of the reasons why those benefits are so impactful. So when we talk to customers about moving to and growing in the cloud with EFS, one thing that excites them, besides how easy it is to get started, is how EFS helps minimize risk along that journey. It's super easy to lift and shift applications onto EFS with minimal disruption. If you're already running applications backed by network file storage today, which is a lot of them, EFS provides the same type of interface that your applications, that your developers, and that your users are already accustomed to. EFS is highly integrated into the AWS larger ecosystem, and those file systems can be shared with tens of thousands of concurrent clients, no matter the type. These could be traditional EC2 instances. These could be containers running in self-managed clusters or in one of the AWS container services like we talked about earlier with ECS or EKS or Fargate. And it can even be in a serverless function that's running in Lambda. Since EFS provides full AWS compute integration, you can modernize your applications on your schedule while gaining immediate benefits from running in the AWS cloud. Once modernized, running Elastic Cloud infrastructure results in further development and operational efficiency, which enables you and your teams to build and deliver more features, capabilities to your customers, and do it in a shorter amount of time. So that cycle of lift and shift, integrate, and then modernize is something we're really trying to drive with EFS. Customers follow a path to modernization by taking existing applications that are on premises or running on EC2 instances and moving them into containers to simplify their deployment and operations. This can also lower compute costs by being more efficient about sizing and allowing those apps to scale more elastically. Because of the native integrations between EFS and both Amazon ECS and the managed Kubernetes service, even applications that need either shared or persistent storage can easily be migrated. With EFS, customers can persist storage across containers, pay for what they use, and create and manage multi-tenant environments in a cloud-native way using IAM authorization and access points. At the end of the day, the idea is that EFS needs to just work, whether it's as a standalone file system or as something that we're using to support applications and workloads. That's the goal. Let's look at some ways customers can leverage this combination of containers and Amazon storage offerings. Sebi talked earlier about building content management systems, right? WordPress or Drupal. If you take any content management system, the idea is to share uploads with as many users across multiple instances. Those users require high availability, high performance, the ability to share data across container instances, and the ability to scale up and down to meet business needs. If we go left to right through this slide, we have visitors browsing the site URL. They're pointed to an application load balancer, which spreads traffic to multiple ECS task instances deployed across multiple AZs for resiliency. And because EFS standard is regional, the instances can easily mount EFS no matter how many there are. The data within those EFS volumes is not only highly available and elastically scalable, it's also shareable. You can make an update and then conveniently access that update across all of the associated containers. You can see in this example, we've chosen Aurora Serverless to hold relational data for the application, making this a completely serverless architecture. ECS or EKS manages the orchestration using managed compute with Fargate. EFS manages the storage infrastructure, and Aurora manages the database. Everything scales elastically, and you only pay for what you use. If we look at an environment like this, let's talk about how we would actually implement this. It is incredibly easy to create an Amazon EFS file system and attach it to an ECS cluster. Let's walk through it using some console screenshots, and we'll show you what I mean. So from scratch, with nothing running, we head into the Amazon ECS console, and we start by creating a new cluster. In this case, we'll use AWS Fargate as the infrastructure provider because I don't know about you, but I have absolutely no time in my day for managing infrastructure.
No way.
I love EC2. I love EC2 instances. I am happy for someone else to take care of those for me. Happy to let AWS do that. I'll focus on the applications. Next, we're going to create a security group for EFS that allows inbound NFS connections on port 2049. We can also isolate this to a specific subnet if we needed to, so depending on what type of security we need, there's certainly availability to be able to do that. Next, we go into the EFS console and we create an EFS file system literally with 2 clicks. Then we go back into ECS and we create the task definition, which is the object that describes one or more containers that are going to form your containerized application. And once we have the task definition in place, everything that we need to be able to mount that file system is right here in the console. You can determine your root directory, you can create your mount point, you can associate the file system ID and the access point ID with the volume, and you're done. Of course, not everybody wants to do everything through the console. And so for those of us who are doing this at scale, or who are using infrastructure as code to manage our task definitions and storage resources, we can use any of the other tools that Amazon makes available to provision this. Here's the JSON for that task definition that we just created, and you can see how we tie those 2 services together by selecting the EFS file system ID and the mount point to attach the file system to the containerized application. We now have a well-defined group of containers which will have access to the EFS volume no matter how much the application scales or no matter how big the user base gets that's accessing that front end. A good example of this is Caltech. Caltech spent years virtualizing their web applications using Red Hat servers, and over a period of 10 years accumulated hundreds of servers. If they needed more scale for existing apps, they deployed more servers. If they rolled out new apps, they deployed more servers. The upgrading, testing, and vetting process to put these servers into production proved to be incredibly challenging and time-consuming, and they had to do all of that through custom code. So to relieve their challenges, they wanted to use containers to be able to do this. However, in their existing virtual server model, both the configurations and the data were stored inside the virtual machine, which made it a real challenge to upgrade. They tried separating out the data and the configurations through partitioning, through configuration management, whether it was CF Engine or Salt, so that the servers were more disposable, but they still faced challenges because both of those data types were still stored inside the container itself. The Caltech team wanted to make the containers completely generic and be able to destroy, recreate, redeploy them however they wanted to. Today, EFS serves as the repository for everything they deploy. Configuration management is complex, and the flat files in EFS relieves them from having to reconfigure everything every time they want to redeploy. They can simply use versioning that they can host in GitHub, and EFS becomes the cost-effective way that they were able to build the generic containers they wanted to begin with to be able to do their rolling deployments or updates. Rather than storing the data and configuration inside the containers, they moved to EFS-attached client data and configuration files for the websites inside the containers, all managed by ECS. Apache, which they were using for the web front ends, would look into EFS for the configuration files every time they started up. So we've talked a lot about containers and EFS. Let's look at one of the other use cases that customers love when we talk about let's put serverless and storage together, and that's going to be Lambda and S3. So S3 Object Lambda lets you add your own code to S3 get, head, or list requests to process data as it's returned to an application. Another way to think about this is basically like inserting a Lambda function directly in front of an S3 request so that nobody notices and it still does all of the cool stuff you want it to. With S3 Object Lambda, you can filter rows, you can dynamically resize images, you can filter object lists, you can redact data from an object or its metadata. There's so much stuff that you can do with it. For example, customers with image sharing applications may want to resize images depending on the requester or the device they're using, like a mobile phone, a tablet, or a laptop. Another example that we see a lot is filtering log data. Logs can get incredibly large, and developers don't appreciate when you drop incredibly large logs on them. What they really want is when they get the log entries they require for their troubleshooting. So, for example, logs that contain specific keywords. In summary, S3 Object Lambda makes it much easier to share and convert data across multiple applications and removes the need to store multiple derivative copies of the data. Let's take a look at how it works. The first thing we're going to do is we're going to set up an Object Lambda access point. This is a new type of access point, and this becomes the S3 endpoint that you will point your application at. You configure that with a Lambda function, and you point it at an underlying bucket using just a standard S3 access point, right? So between the Object Lambda access point and the S3 access point is where we're going to put all the magic. Now that Lambda function is provided by you. We've got some examples in the documentation to get you started, but fundamentally you have control over how your data transformation is going to work. So when a request is made to the Object Lambda access point, what it does is it runs around and invokes that Lambda. It pulls the data out of S3, processes it according to the code that you've provided, and then streams it back to your application. That processing happens totally in line with the request. So as far as your application is concerned, it just did a standard GET request against a normal S3 access point. And that's pretty cool. Any other request that comes in, any request that's not one of those ones that we're going to be able to use the S3 Object Lambda for, is just going to route around the Lambda function. The Lambda function is not going to get invoked. The customer's not going to see any charges for it. A great example of this is Ryanair. In March of 2021, Ryanair launched a new COVID-19 travel wallet, which was available from their mobile application. Ryanair customers can use the COVID-19 travel wallet to upload negative PCR tests, COVID vaccination certificates, any other COVID documentations that may be or were required for EU travel. That documentation is uploaded by customers and is securely stored inside S3. And here's how they used Object Lambda for that. First, the mobile app requests information for the reservation. The API gateway triggers AWS Lambda with the information supplied, and then Lambda generates the boarding passes and S3 URLs for the PDF COVID files. The app requests the COVID documents using that return to S3 access point URL, right? Just like we're 100% vanilla S3 at this point. And then Object Lambda checks if the PDFs have already been converted into images. So if it responds with, yes, I already have the image there, it'll just return that image to the application. If the Object Lambda comes back and says the PDF has not already been converted, then Lambda will convert it, will store it in S3, and will then respond with that new image. By shifting this logic to AWS and leveraging S3 Object Lambda, Ryanair was able to include PDF files, allowing customers to upload PDF files without any app changes in under 3 days. And customers today can use that Ryanair mobile app to move through a booking quickly. Obviously, there are dozens of other use cases where serverless and storage is going to be the right answer, and we don't have time to go through all of them today. But I encourage everybody who's watching, if you want to dig into this, if you really want to start to see some of the customer examples, see some of the technologies that we're using, see some of the ways that these things can put together, there's a link in a QR code that's on the screen right now that goes to an entire list of resources, websites, different marketing resources, different sales resources that AWS has in order to be able to help out with this. I really appreciate Sebi letting me come on here, letting me help out with some of the examples of how that we can use this and how we can deliver it. And I hope that we gave you some ideas that you can use on how to accelerate the application development. And really, we want you to build amazing things with AWS, and hopefully we did a little bit of that. So stick around for our next session, and we really appreciate you for watching.